Today we're going to talk about complex numbers and their operations. So far in this course, you have worked within the set of real numbers determined by real number solutions. So we're going to introduce you to numbers that are not real. It says, consider the equation x squared equals -1. Is there a real number solution? So let's think about that. When we solve from an x squared, we take the square root in order to get rid of the square. And I do that to both sides. And so the square root and the square cancel. But then we end up with this negative under the square root. And so previously, you were told no solution. This is really no real solution, because there's nothing that multiplies times itself to give us a -1, because -1 times -1 is a +1. So that is where the imaginary number I comes from. It is a number such that I squared equals -1. So if I squared is equal to -1, and we took the square root of both sides to get rid of that square, then the square root and the square would cancel, and I would be equal to the square root of -1. And so that is the definition of I. I is the square root of -1. You'll see this a lot on SATs and PSATs sometimes. Well, they'll do like I squared. Well, if you think about I squared, we would square this right here, and so that's equal to -1. And the pattern actually repeats every 4, so it's easy to figure out which one it is. Because I third would be equal to negative square root of -1, and so then I to the 4th, we would square this and it would be equal to 1. And then the pattern repeats from that point. All right. Now that you know about I, you can rewrite expressions involving negative roots. For any positive real number n, the principal square root of a negative number, negative n, is defined by I root n. So if we have the square root of -n, it is I square root of n. So the square root part, we're going to do exactly like we've done in the past. The only difference is that we separate it to get that -1, which is our I term. All right, the set of imaginary numbers is the set of all numbers written in the form a plus bi, where a and b are real numbers and b is not equal to 0. A pure imaginary number is a number of the form bi, where b is not equal to 0. So this is going to be a constant, and this is going to be a constant. So this is the real number part, this is the imaginary number part. And so that is a part of the complex number system. And so the complex number system includes all of our real numbers and our imaginary numbers. So a complex number is a combination of a real number and an imaginary number. In this course, we're going to use imaginary numbers to solve quadratics. All right. So you know how to perform the basic operations of addition, subtraction, multiplication, and division on the set of real numbers. You can also perform these operations on the set of complex numbers. When operating with complex numbers involving I, combine like terms by treating I as a variable, even though it is a constant. So I is not a variable, it's an imaginary number, so it's going to be one value. But we do treat it as such when we do operations on it like we've done. For example, if this was 3 plus 2x minus 1 minus 6x, we would treat it in the same fashion. So I distribute this negative sign here, so we get 3 plus 2i minus 1 plus 6i. And then we combine the like terms. So my real numbers will be combined to give me 2, and my imaginary numbers would be combined to give me 8i. So this would be 2 plus 8i. We usually write the real number first, that's that a part, and then the imaginary number second. So here's another one. We would want to combine our like terms of 4i and I, and then our constant of real number of 3 minus 6 minus 1. So 3 minus 6 is -3, minus 1 is -4. And then a 4i plus an I would be a 5i. Here we've got 4 minus 10, which is -6. and 7i minus 2i, which is a positive 5i. And then for our last one here of like terms, we get -4 and 7 gives me 3. And -2i minus 6i gives me a -8i. So we did the same thing as if there was an x there. All right, now when we multiply, you can multiply an imaginary number with a real number. In this case, we do not add or subtract a real number with an imaginary number, but we can multiply them just like if it was 5x times 3 minus 2x. You can multiply those. So we distribute here. 5i times 3 would give me 15i, and then 5i times -2i would give me a -10i squared. 5 times 2 gives me the 10, and then I times I gives me the I squared. Now, on the other side, we said I squared was the same thing as -1. Therefore, I can simplify this. I can say 15i minus 10 times -1. This will give me a positive 10 plus 15i. All right. Right here, we've got two binomials being multiplied together, and so we know we simplify that by FOILing or distribution. However you multiply, that's where you multiply your first, and then your outside, your inside, and your last. So 5 times 2 gives me 10. 5 times -3i gives me a -15i. 3i times 2 gives me a 6i. And 3i and -3i give me a -9i squared. And so to simplify, remember I squared is -1. And so -1 times a -9 gives us a positive 9. And so when we add that together, that gives me a 19. And -15i and 6i give me a -9i. All right, for our next one here, 2 plus I, 2 minus I, we're going to FOIL that. 2 times 2 gives me 4. 2 times -I is -2i. Then we get a 2i, and then we get a -I squared. Remember, this is -1. And so a -1 times the negative gives me a positive 1. Plus the 4 gives me 5. And a -2i and a positive 2i is 0. So this is just 5. We knew that was going to happen with the middle terms canceling out since this is the difference of two squares. So recognize those patterns and it makes things a lot faster. Just like this one here is the difference of two squares. So my 3i and my -3i are going to cancel. So this is only going to be 1 minus 9i squared. Now I squared is -1, so that becomes 1 plus 9, which is 10. Why don't you go ahead and pause the video and see if you can do those two right there. Those are similar to the ones we just did, and see if you get them right. All right, check your work. You should have gotten 13 and 41 there. So our next question here says, what do you notice about each product in parts C and through F? They are the difference of squares like we talked about, so therefore they end up with only one I term. That is squared, and I squared is equal to -1, so it simplifies to only a real number on that one. So we got a real number on all of these because they were the difference of squares, and so those middle I terms would cancel out. All right, the last thing we're going to talk about here, it says you may have noticed that the products in question 5 parts C through F did not contain an imaginary number, even though the original expression contained an imaginary number. Each pair of those expressions in question 5 are called complex conjugates. So they were difference of squares, but there's a name for those. It's called complex conjugates. Those are a pair where you have A plus BI and A minus BI, those two right there. The product of a pair of complex conjugates is always a real number and equal to A squared plus B squared. So here we're going to look at what our complex conjugates are. We will use those in pre-cal, so you want to understand what a complex conjugate is. If you have a 7 plus I, its conjugate would be 7 minus I. You are only changing the sign of the I. So something like this, where it starts with a -5, that -5 is going to remain, but it's going to turn into plus 3i there. And then this would be 12 minus 11i. And a negative 4i would be a positive 4i. So the complex conjugate is when you are changing that other I to a negative value. Then it becomes the difference of squares, which allows you to clear out the I values. All right, those were operations with our complex numbers.